Welcome to the Podkey summary of Secure Your Apps with App Attest from WWDC 2026. A lot of this comes down to one simple idea. If your server can tell it's talking to a real app on real Apple hardware, a whole category of fraud gets much harder. The new App Attest details in iOS 27 and macOS 27 add more context around where an app launched from, which binary version is actually running, and whether repeated requests still look trustworthy over time. And the practical part matters just as much as the cryptography. Key handling, replay protection, rate limits, and knowing when a weird signal is actually fraud versus somebody just reinstalling an app. At the high level, App Attest is there to stop modified client apps from quietly pretending to be the real thing. Think about a quiz proctoring app sending fake answers, or a game client with a cheat menu injected into it. If every important request has to carry cryptographic proof tied to genuine Apple hardware, the server has a much stronger way to say no. That proof tells the server the app is running on an untampered device, and it lets the backend reject payloads coming from a re-signed or otherwise altered binary. It also surfaces details like the relying party identifier, launch validation category, and bundle version, which helps catch someone who changed provisioning or bundle metadata to make a fake copy look legitimate. The big addition here is extra data in the authenticator information for both attestations and assertions. Servers can now see a launch validation category that says whether the app came from the App Store, test flight, or an extension. That sounds small, but it's a very useful reality check. If you run a production-only app and requests suddenly show up from test flight, that's worth a closer look. There's also a bundle version field, which tells you the exact version of the binary running on the device. So if your shipped version is one thing, and the server starts seeing an unknown or mysteriously newer bundle version, that can point to a re-signed copy or other tampering. The useful move is to read those fields together. A test flight launch by itself might be fine in some environments, and a version mismatch might have a harmless explanation, but stacked together with other odd behavior, they become a pretty solid risk signal. On the implementation side, the guidance is pretty straightforward. Create one secure enclave-bound key per user or per app on that device, and don't share keys across users. Store the key ID securely in the keychain, because that ID is how your backend keeps track of the device-specific trust relationship. These keys survive app updates, which is nice, because routine updates shouldn't look suspicious. But they do get invalidated on reinstall or device restore. So if a key disappears, your server shouldn't immediately treat that as fraud. Sometimes it just means the user did the most normal troubleshooting step on earth and deleted the app. Key IDs are also specific to each device, and they don't sync across a person's devices, which keeps the trust model clean and makes server-side management simpler. For ongoing requests, one of the most important checks is the assertion counter. Each assertion carries a monotonically increasing counter, and the server should verify that it strictly increases for that user or device record. If the value stays the same or goes backward, that's a warning sign. It can mean the client is compromised, replaying old assertions, or otherwise out of sync with what the server believes is happening. This matters even more because assertions are generated locally and don't need a round trip to Apple every time. So the counter is your main anti-replay guard for high-frequency traffic. There's also a fraud metric that gives an approximate count of unique attested keys linked to a device over the last 30 days. That can help identify devices acting like brokers for lots of modified app instances, which is the kind of sentence that sounds niche until you realize how many abuse problems boil down to exactly that. The advice here is not to auto-block on that number alone. Establish a baseline, watch for spikes, and use sudden jumps as a reason to investigate further. And keep context in mind, because reinstalls and device restores can increase that metric too. Weird doesn't always mean malicious. Something similar applies to the unsupported API. If App Attest suddenly starts reporting unsupported for a particular user over and over, that may suggest tampering or execution in a non-Apple environment. At that point, developers have to choose the response. Maybe degrade functionality, maybe restrict access, maybe run extra risk checks. It's a security decision, But it's also a product decision, because too much friction can punish real users faster than it stops bad ones. One more practical piece is rate limiting. Back-end services should be the ones initiating attestations and enforcing request per second caps, so they stay inside Apple's global rate limits. If you don't do that, a spike in attestation traffic can turn into its own outage, which is a pretty frustrating way to discover that security systems also need traffic management. On the app side, retries should use exponential backoff, and attestation work should run in background tasks instead of sitting in the middle of user-facing flows. That keeps the experience smoother for legitimate users and lowers the chance that a burst of retries trips throttling when something upstream is already having a bad day. The overall theme here is layered trust app. Attest gives you strong proof at the device and app level, but the real value comes from combining that proof with sane server checks and a little operational discipline. If the signals line up, great. If they don't, you've got better questions to ask before a fake client gets too comfortable. This episode was generated by Podkey. Create your own at podkey.fm.